If this is the talk that you hope to be in, then I'm glad that you're here. Understanding the Constexpr two-step from compile time to runtime. This is one of the more difficult talks I've put together. I'll explain why. That's my title slide, by the way. Phil makes me put in his, but that's mine. My slides are very simple. I don't go for pretty slides, but if you've seen any of my talks, you know that already. So my name is Jason Turner. I am host of C++ Weekly, and I have some open source projects and some books and stuff, and I have to have the obligatory About Me slide, but I also have a couple of little 3D printed swag things that I made for my YouTube channel, so if I get some like awesome question or feedback, then you might get one. I also have stickers up here if anyone wants some after the talk. Yeah. I'm still waiting to see if my MVP got renewed for 2024. We'll see. I do training and code reviews. This is what I do. I'm independent. So if you like these talks, then strongly consider having me to your company. I know there's at least a few people here who have been to my corporate trainings or have been to my classes, workshops at conferences as well. I say move to the front. There's some of you sitting in the back. Come on. All right. No, I also sit in the back, just for the record, because I like to get up and pace. So, but regardless, interrupt me and ask questions. This is a good room for this kind of thing. The only thing I don't like about this room is I also like to jump off the stage and interact with the audience more personally, and it's a little dangerous here for me to do that at this height. But if you do like this stuff, this is about what my training days look like too. All right, so for this talk, I went to an extreme effort to try to fit meaningful and readable examples on single slides. What you'll see is, except for the last example, I have managed to fit everything into a standalone compilable example in 30 lines of code, including the pound includes. It might have been a mistake in a couple places. So hopefully this works out. There's more code than I tend to put on slides, but interestingly less assembly than we sometimes talk about. And if you don't ask questions, then I'll probably move too fast. So I'm counting on you. You. Okay. All right, so C++20 gave us Constexpr containers. And those relied on Constexpr new and delete. These features were added in C++20, but it took until GCC 10, Clang 10, Visual Studio 16.9, 2021, before we had Constexpr new and delete available to us. And we didn't actually get these containers until 2022, basically. So this was a little bit late coming for a C++20 feature. So who is familiar, like, at all with this? Have you, Vector became Constexpr in C++20. Does that ring a bell to anyone? Okay. So if Vector is Constexpr in C++20, then I can do this, right? No, okay. So who here has actually like tried to use vector and string in Constexpr code and real code? Who has successfully used vector and string in Constexpr code? Is it really that big of a difference? I was expecting a slightly different, like at least some of you. Okay, so attempted versus successfully did it. Okay, so vector is Constexpr, but not how you expect it to be, basically. If I try to compile this, then I get this error, which if you were watching Dave's talk, talking about 50 pages of compiler errors, this we will dig into this, but pointer to sub-object of heap allocated object is not a constant expression. It's annoying. So, vector is Constexpr, and I had to meme it. So that means we can have a Constexpr vector, right? No, we can't. Not really. Well, let's take a closer look at it. Does this compile? Does anyone know? Who says it does compile? Who says it does not compile? Who says, I don't know? Okay. This does compile. So what is happening? Effectively, memory allocated at compile time must be freed at compile time. This is effectively the rule. I considered like quoting the standard from here, but it was too much effort. So if we go back to this, have I allocated any memory? Not necessarily. In a good implementation of vector, have I allocated any memory?
Yes, because of the links around the lot of data you're dealing with vector. This is always the go with it.
Oh, but this is, I mean heap allocated any memory. With new or delete is the question. So as opposed to stack object. So there is stack data here, which is the vector implementation itself, which is approximately 3 words, says one of the C++ trainers in the room. All right, does anyone know what those 3 words are? What? Pointer, size, and the allocated capacity. Yeah, the reserved size of it as well. So those 3 things definitely have to live on the stack here, but presumably they're all 0 right now, right? I think that would be fair to say. Again, in a good implementation of vector, not one that allocates just for the fun of it when it's empty. Okay, so back to this one. So I have a Constexpr function that is returning a pointer created by calling new with a new expression. Is this a valid function? My shoe got untied. This is a function that will compile. This is valid. We will build on this. I just have to tie my shoelaces so I don't trip. And I also am doing my best to make sure the camera crew stays awake. Okay, so now I have my useData function that is calling makeData. And note, I am dereferencing the value on line 6. I am intentionally leaking. Do you expect this code to compile? Remember, I'm not allowed to leak memory at compile time, but yes, this does compile. Okay. Now I am actually calling this function. So main calls useData, which is a Constexpr function, which calls makeData, which is a Constexpr function that does this thing. Yeah, it's all good. This row likes this code. Well, I mean, we could have fun with this. How much time do? Okay. Is this a memory leak? What? I definitely will get students that will argue with me that this is not a memory leak because we know for a fact that the operating system is going to clean this up when main exits. Okay, but also I have to do it. I have to do it. I'm required to do this. Where did my new go? With modern compilers that can optimize out heap elisions, I'm just getting return 42 from main right here, and the compiler optimized away the memory leak. But let's not spend time on that right now, shall we? Okay, that compiles as we saw. Okay, so now I am assigning this thing to a local integer I. Compile. Okay, yes, this will still compile. It's no different than the last one. Okay. Now I'm assigning it to a Constexpr integer I. Now it fails to compile. Because now I have actually pushed this computation, even though it was doing it at compile time anyhow, as an optimization choice, now I'm saying it must be done at compile time, and the compiler is saying, no, sorry, you're not allowed to leak memory at compile time. Okay. So, how do I make this valid? And that is effectively the point of this talk. Here is a way to make this valid. And this is what I have decided I want to call the Constexpr two-step. I have something, well, wait, I have slides that break this down. Look, I can highlight the code. I do something with dynamic storage at compile time. Some dynamic thing. I am calling new here. That's step one, do dynamic thing. Step two is to then make a copy of that dynamic thing for runtime use. And then I don't have this listed as step three, but you do need to still clean up after yourself, okay? So this is clearly a silly slideware example, right? I hope you're not writing code that's allocating new integers just to return the value 42. But this is the key. Step one, do dynamic thing. Step two, copy the dynamic thing to statically sized thing. And I have to be careful with my terminology here. By static, I don't necessarily mean static as in for the lifetime of the program, globally scoped static, but we will do that as well. But I mean like compile time sized known thing versus dynamically sized thing, all right? So that is it. Okay, so this is the Constexpr two-step. We do all the dynamic stuff that we want to do at compile time, and then we copy that into statically sized things. All right, so. How much time do we have left? 40, oh, okay, sorry. 45 still. No, I'm just kidding, of course. So this is the goals for this talk. Level one, we will go from taking a vector and returning a Constexpr oversized thing. And you'll see why it has to be oversized. Right sizing it is well, that's a later thing. Level two is to be able to take a string at compile time and return a Constexpr string view into the data that was that string. Level three is to take a vector of something and now right size this thing. And we will demonstrate what this means. And then level four is to do something that is multiple layers, such as a vector of strings, and be able to return a Constexpr span of string views into that thing. I feel like I'm gonna get some arguments with how I did this last one, assuming we get there. All right, so this is my oversized array. You know, I was just editing my slides during the last talk, as one does. And I was questioning the use of the name oversized array here. So please push back and ask questions if you, it's a fixed maxed size vector. The idea is that it has a max storage size and it lives on the stack. And, but the actual like current size of the thing is a runtime value, right? So it can contain between 0 and capacity elements. And it has a begin and an end So it is iterable. Note, begin and end are necessary for iterability here. And this is a relatively compact thing, but I tried to be nice with best practices here. So I've got no discard, Constexpr, const no accept. That's what your normal function declarations look like, right? They should. Okay, and I tried to do, the nice thing here and avoid pointer arithmetic, so I'm using standard next, but then slightly annoyingly, I actually have to cast my size to a pointer diff t, so that standard next doesn't give me a conversion, whatever. So that's the idea, okay? Does that make sense what this thing is? There's no pushback because I needed it to fit on a slide. I could have put a pushback on here. It would have been easy. It would have just assigned the next element at the current location and size and then increment size, right? That's one line of code. Oops. Okay. Does anyone have a better name for this than oversized array? What? Finite array? What? In place vector? A what array? Bounded array? Capped array? But you're all still calling it, well, I don't know. It's just array in C++. We assume a fixed size, whatever. Okay, so I just removed no discard and no accept, and I went back to pointer arithmetic so that I can get these things to fit on further slides, okay? And then I also combined the two member variables, data and size, onto one line. I have further slides I'm not very proud of. Okay, so this is an idea. This is something that kind of came up when I was working with some physics students and we were talking about Constexpr stuff, and they liked this example even though it's not 100% relevant to their code. That I want to be able to create some sort of vector of angle divisions. You tell me how many angles you want divided 360 into, and then I create a vector, I push back however many you asked for, and I return the vector. Plausible example for something I might want to do at compile time? Okay. Here is a version of it that takes the count of angles as a template parameter because I expected someone to ask a question about this. So in this one, I don't have vector shenanigans to worry about at all. This is just an array of doubles, and I know the exact size, and I'm able to just build the array and return it. Thoughts? Pros, cons, comments between these two different versions?
You cannot use it at runtime, the second version?
You can't use it at runtime. Yay! Thank you. Yes. So basically, I cannot use a runtime known parameter with this. So yes, it is totally doable that if I want to bake in with template parameters all the perfect sizes of things, I can do things this way. But we want to talk about this note that I don't like applying the term metaprogramming to Constexpr. Constexpr functions are just normal functions that you can also coincidentally happen to be able to execute at compile time. That's how I want to think about Constexpr. All right, level 1, attempt 1. This is where we look at the examples. Okay. You can see the comment at the bottom. This has a bug. I have my oversized array, lines 5 through 9. It's been squished down as much as possible. I have my angles function, 11 through 15. That's the one we were just looking at. Then I have this helper function called toOversized. You pass a vector into it, and it creates this local oversized array right here on the stack. And then on line 19, I copy the values from the vector into that array, then I return the array. So then on line 24, down in main, I've got a Constexpr static array of the elements that were created by calling make angles. You see the bug, Arna? Wait, what do you see? The capacity is too small. What happens? What does this do? What do I have? Do I have undefined behavior? Do I have what?
What does the next violation of Python look like?
It looks like, well, I have to actually walk back over to the computer. So I have in Constexpr expansion of this function, make angles, blah, blah, blah. This is very readable. Here we go. The actual error that I get is array subscript value 255 is outside the bounds of the array type of 255. So what it tells you is that I tried to access the index 255 of a 255 sized array, which would be the 256th element at compile time, and that is undefined behavior. I can't write off the end of this array at compile time, so the compiler fortunately stops me from doing this. We're not allowed to have undefined behavior at compile time. That's good. Okay, so do your job, remote. Okay, so attempt 2. I now have passed the max capacity forward as a template parameter. So now I can say 2 oversized 512. Now, I know that reading this code, you would say, why don't I just go ahead and say this is 300, right? Because I know the exact size. But the problem, I want you to be thinking more generically, less simple slideware, okay? So this does compile, but now I have a capacity of 512 here for a thing that's holding 300 angles, and I can print them all out. This is where we should take a moment and actually look at the binary for a second. And if you care, I can prove to you that this code does actually execute and print what I want it to. Look, we get 300 angles printed with very well done formatting. Okay, so I'm gonna flip over to Clang because I like its assembly better, it's prettier. But we can see that I actually did generate a table of 300 angles. And I can mouse over any of these things or look at the comments that the Clang compiler put in for me for what these hard-coded doubles are inside the thing. But something we need to call our attention to, and we'll look at more as we dig into this further, is this very bottom bit. I have 1,696 zeros left over. So if I'm not careful with this technique, I can absolutely bloat my binary size. And then the very last thing is just fun to look at. That is the actual used capacity of this thing, the actual size of this thing is 300, exactly like I expected it to be. Any questions on this? Are you sure? Have to vote and see who gets the swag toys. All right.
Sorry. When did this get declined? Because one of the common things I'm hitting in terms of Android specifically
Uh-huh.
is, version of client that Android using doesn't support this feature of, I mean, Aviate C17 things it doesn't support.
Right.
What version of client?
So the question for the YouTube audience later is, what version of Clang did this actually come in? And I'll reference back to that. Where did it go? That chart right there. So you actually get vector with Constexpr. Clang 15 is what I have written down here. For Clang standard library, libc++. I think I'm almost positive that's right. I did specifically look up the release history, and I tried to get this right. But what standard library actually ships with the Android tools dev kit or whatever? I don't know. Does anyone have any idea when you would be able to do this with native Android code?
You see the concern that I have with this one. It's going like, I'm constantly thinking, I can do this. Oh, Clang says no.
Yes. Yes, this is more, well, it's one reason. So the comment was, Clang says, no, you can't do this in their environment that they're trying to work in. And that's one reason why I thought that this was appropriate timing for this talk, because people are just now really starting to use versions of these compilers that will allow you to do these things. So in like maybe 6 months, you'll be able to. Hey, it's better than my students who work on like giant government supercomputers, and they're like, oh yeah, we'll get that compiler on the 5th of never, or whatever. All right. Oh no. Have to get back. Okay. Level 2. All right. Level 1, attempt 2. So this is a complete compilable example. We just saw it. Is it good? Okay. If you have questions, though, definitely stop me. All right, so level 1, we successfully copied from a dynamic storage thing to a fixed size thing. Yes, it is simple, and we could clearly see the needed sizes. And like I already said, I'm trying to get you to think more generically. And yes, we can unfortunately bloat the binary size if we're not careful. All right, so checkbox, level 1. Level 2, from string to Constexpr string view. What is a string view? Fundamentally. Pointer and a size. How do I ensure that my string view is used safely? Well, pass by value is more about using it efficiently than using it safely. A more fundamental problem. Do not store it? No, I want to store it. That's the whole point of this talk. Yes. The string still has to be alive. I have to ensure somehow that the string that I have created a string view into outlives the string view. That is the fundamental problem. So you can store string views as long as you know where the strings are and that they don't move. No, they can still move. That doesn't sound like a good idea, though. Okay, so our data must outlive the string view. So we need some sort of data store that's going to outlive our string view. Do we happen to have one in our examples already? My oversized array, okay. I can just make a car version of it. It's templated, yay templates. Okay, so I have my make string view function. And I'm receiving a string, I am creating my oversized array, I am copying the data, and then I am returning a string view into that array. So I am returning a reference to local data. You said random ASCII characters. Did I get that? Is that what you said? What is 40? This one right here? Oh, sorry. So I am, yeah, I should have pointed that out when I was reading the code off. Just to make a string that is dynamically sized for the sake of getting this to fit on one slide, I am calling one of string's 18 different constructors. And how many constructors does string actually have? 14? Something, 17? It's a lot. It's a lot. So I'm calling the constructor to string that takes a count and a character. So theoretically, I will have a view of 42 A's when I'm done here. But I also kind of gave away the answer. Did you see it though? I am returning, it's the exact problem that we were just talking about. So Jan, you should have said something. I'm returning a string view to this array. That array does not outlive the string view. And so, you get fun output like, it's always fun and different, like this. That's how you know you have a well-defined behavior in your program. That's a joke for the recording later. Okay, so now I have created on line 13, I've swapped this around, so I'm creating a Constexpr oversized array and then returning a string view into that oversized array. This is the part where I expect at least one of the people who came to my workshop yesterday to see the bug in this code, the problem with this. Do you expect this to be good? Who expects it to be bad? Why? Come on, anyone. Wait. It's the same as before, but a lot of people get this confused and they think that Constexpr somehow affects the lifetime of the thing. It does not. This is the same problem exactly as before. Making it Constexpr, actually, sorry. This is a different bug still. This is a different bug. It's a different bug. Did you see what the answer was? I'll find it now, though. Shh. Most of you said no. This is important. This is like super important. And I totally forgot the slide was here. Yeah, what is that? Yeah? Wait, on 21? No, that's not the problem. This code fails to compile. Yeah? Yeah, Arna, are you?
By reference capture of the...
Yeah. Reference capture the input. That's not specifically the bug. This one trips everyone up when they're trying to do compile time stuff with Constexpr. Yeah. The input is constant. Wait, on line 4, so what's the problem, sorry? Yes. Yes. Oh, no, the copy is copying from input into the result. It does it the right way around, not like memcopy.
But the lambda is still returning in the temporary.
The lambda, no, the fact that I'm returning, that's fine. The lambda is immediately invoked. It's returning that local value. I'm going to get return value optimization. That's good.
When determining the value of that.
Yes. Everyone heard that, right? No, I'm kidding. Okay. Input is not Constexpr. Input is just a regular function, a regular parameter, and I am trying to use it to initialize a Constexpr value. As of C++26, as far as I still know the rules, function parameters are never, ever constant expressions. So I cannot use them to initialize a constant expression. Okay, sorry. So now I rearranged things so that I have const auto input equals make string. So now I'm calling this function, it's no longer a function parameter, I'm calling the function down inside the lambda directly, and now I may as well just go ahead because I'm moving too slowly. I need to move faster. This is back to the same problem again, that I still have that reference to a local. Okay. So if I make this Constexpr, so in these cases where I'm returning references to local things, if I initialize this string-like thing down here on line 22, excuse me, if I declare it as Constexpr and I force the evaluation of all this at compile time, then I get a compile time error on line 22 saying that I have a pointer to stack memory that's already gone out of scope. That's great. But now here's where I want to challenge you again in a second. All right. When making your data to view converters like I am presenting in this talk, prefer to make them consteval. So if I make this thing consteval on line 12, if I declare this function consteval, that is saying this function must be evaluated at compile time. It's also known as an immediate function. And by saying it must be evaluated at compile time, I don't even have to make the object that I'm assigning it to const or constexpr or anything, and it will fail to compile. There's another bug in this code, but I don't expect anyone to see it. I thought that I had found a bug in Clang. It's a bug in Clang, not a bug in the code. So we'll get to that in a second. Sorry, in this version here. Right, so that fails to compile. Now if I make this thing constexpr static, and then I'm returning a string view into the constexpr static and make this consteval, everything works exactly like it should safely. And it's guaranteed to be safe. If this code compiles, it is correct when I made it consteval here. That's neat. All right. So I've just rearranged the code, and I've tried a little bit from time to time to rearrange things so that you can get a different view of them, and hopefully it all makes sense. But I have a constexpr static auto, and this is just doing the exact same thing inside of immediately invoked lambda. So I am executing my make string function, I am doing the copy of data into the oversized thing, and then I'm returning that oversized thing, and then I'm creating a constexpr static string view into that oversized thing. Does this make sense? All right, I'm getting enough nods that I'm gonna move forward. Okay, so this is annoying though. I've just had to bake in the operation that I wanna perform. And I have two potential ways to move past this. I have two options here for what I am calling my toView function, and I'm calling it a builder. I'm passing in a builder callable of some sort that executes, creates the dynamic thing that I want it to create. And on the first one, I am taking the builder as a template parameter itself. I'm using auto template parameters. These things are super fancy. Pass callables as template parameters. And on the bottom one, I am just using a regular auto function parameter. Just for the record, I'm assuming that if you're doing any of these techniques, you have at least cplusplus 20 on your compiler, okay? Now, there are pros and cons to both of these. Calling the bottom one, actually, you pointed out that function parameters are never constexpr. Can the bottom one work? You're right. I thought I copied it from working code though. So now I'm slightly confused. But you're right. I didn't capture the parameter. If I'm capturing the parameter, yeah, You can, basically you can if the thing that you pass to it was a Constexpr function itself. So if I try to do something like this, like pass a lambda with a capture, it's even though lambdas with captures can be callable in a Constexpr context, it's not treated the same way, and that's the level of detail I'll go into at the moment. But the template parameter version actually ends up being the more versatile one, where I pass the callable thing as a template parameter in the top block. So that's what we will have in some of our examples too. The bottom version doesn't compile. All right. So this I definitely don't have to capture because it's a template parameter. So this definitely does compile. So this is now the builder thing. And so when I call my toView down here on line 24, sorry for the sake of YouTube viewers, when I call toView down here, I am just passing a lambda thing that performs the operation that I wanted to perform. It could be a free function just as well. Does that make sense? So now I've moved that action out of the toView function, and now I can call this with anything that generates a string. All right, so to review, to make sure that we're all on the same page here, I have step one, I am calling the toView function with the operation that I want to make into a compile time known view. Step two, I actually execute said function. Step three, I create this oversized array, initializing it. So it's this, by the way, I didn't explain this at all. But again, I'm trying to avoid having too much code on the screen. So I am initializing the data to nothing, and I'm initializing the size to whatever input.size was, so that that information will be kept. And then I do the copy, and I return that, and now I can safely return a string view into that Constexpr statically generated thing. Yeah? Okay. Like I said, I don't know if this was a mistake to put as much code on the screen as I did. Okay, what's kind of like a string view but isn't, and it was added in C++20? Span. All right. So, level 2.5, span and string view. I have now enhanced my oversized array thingy and given it constructors. So exciting. So I have the first constructor on line 4. It takes a range concept and a Boolean indicating whether or not it was constructed from a string. And then my second constructor on line 9, if I receive a basic string, then I just forward that to the other, delegate it to the other constructor, and I pass it true, this was a string. And then if I receive a vector, I, again, delegate to the other constructor, and I say false, not a string. So I can handle string and vector separately. Otherwise, my begin and end stay the same, and I've just added this extra thing here, bool, whether or not it's a string. Okay, like I said, trying to fit everything on one slide, I did. My limit is 30 lines of code. Otherwise, it doesn't fit. So there is the oversized array thing from line 7 to 16 that we just talked about. And now my toView got a little bit smarter, but also a little bit simpler. Static, Constexpr, auto, OSS. I don't know what the type of this thing's gonna be. Auto is great use case here. And then OS here, I simplified the name of my oversized array, so it's just called OS. So I'm saying construct an oversized array from the result of this builder. And if the constructor that takes a basic string, a string is called, then it does what we just talked about. If the constructor that takes a vector is called, it does what we talked about. And in both cases, it uses class template argument deduction to sort out the details for me. All the features come together. So now on line 28, I can call this thing with a function that returns a string. I'm going to get back a string view. On line 29, I can call the function that something that returns a vector. I get back a span. Questions? Does it make sense? Okay. So note, I did find a bug in Clang. While I was working on this, I thought that I had discovered a new bug, but it was Matush, who is here, but he's also speaking right now, so he's not in this room, who found this bug back in March originally. So there's links to it if you care about this later. And the bug is right here. Clang tries so hard to make sure that consteval immediate functions do not get emitted into the binary that it even removes any static data that was inside that consteval function. So if you want this code to be portable, you cannot have static Constexprs inside of consteval. You don't get a warning. You don't get an error. You just get the wrong output when you try to execute the code later, just so you know. So we have a fix for it. And the fix in this case is no longer to use an explicit static. It is now to use a template parameter again. So my toView takes my builder and it uses that builder to instantiate an object of type OS. And notice that that is now itself a template parameter. That becomes this value parameter here, and this is effectively a static. I can now create pointers into that compile time known template data parameter. I'm seeing some people that are like, why am I still sitting here? Some people that are like, what did you just do? This is totally valid code, and again, the fact that it compiles means it's right because it's consteval. I love code that compiles when it's correct. All right, any questions about this? Yeah.
For the view helper function, the template parameters, usually it's OS value. OS is a customized, you define OS type.
Yes.
You can do this as a value. You can put arbitrary, you can specify the type of your template parameter.
Yes, you can specify, actually, I don't know the exact limits there, but I can specify the type as, and notice,
Because usually you can say template it's a
yeah, so this is, it's like, well, I did an episode on this recently, and it's called CTAD for CTAD for NTTP. So this is a non-type template parameter. The thing called value is a non-type template parameter. It is a user-defined type, and it is relying on CTAD, class template argument deduction, to know what actual type of a template instantiation it is there. So I give it the name of a template, and the compiler sorted out the rest for me. All right, I have to move faster. Okay, so level 2.5. So we can break it down. I'm just gonna break down creating the string view version. Step 1, I pass the callable thing that I want to invoke as a template parameter to view. Step 2, I use that callable thing to create an object of type OS. I pass that as a template parameter to view helper. I know which constructor I called. And then step 5 here that we didn't really talk about is this if Constexpr. So because this thing, value, is now a compile time constant, it is a constant expression itself, I can do an if Constexpr and make a compile time choice. And I can say, if the thing that was originally constructed down here on line 28, if it was a string, then I'm gonna return a string view. If it was not a string, then I'm going to return a span. Okay. So, this is really the crux of it right here. So we can slow down for a second. I want to get to step 3. I didn't expect to get through all 4 levels, just for the record.
I was trying to work out exactly what the template parameter was doing, given that you were passing it as a template and not as a parameter. But now it makes a bit more sense because you're able to, at that point, have it, because of being a template, the constructor can then work out what the constant evaluation becomes because of you're using that particular use of essentially helper to deduce whether it's a string view or a span in that particular instance of it.
In this particular instance of the template parameter that was passed to me, yes.
So, and of course, because the idea is it will produce different versions of that template.
Yes.
Each use of it.
Yes. So every time I call view helper, it's going to be a new template instantiation, unless I happened to give it something that had the exact same values as the previous one. And whether or not your compiler is actually going to memwise this work, if you know what that means, like, will the compiler say, hey, wait a minute, I've already seen this exact same template instantiation before, I know what to do here? I'm not 100% sure. It might do that. You might do the work twice. Okay. So let's get to the right-sized array. So how do I get from the oversized thing to the right-sized thing? Any ideas? What's that? Return the size as a parameter? As a pair. Return the size as a pair. I don't have to do that. I can, but I don't have to. Arne, go ahead.
Basically, use the trick you use right now and pass the oversized array function pass.
Mm-hmm.
And then you just compile the actual size for the array.
Pass the oversized array, compile time, okay, and then deduce the size of the thing. What were you going to say?
Conversions between oversized arrays which have different sizes.
Conversions between oversized arrays that have different sizes. You're all kind of in the right ballpark. It's actually way simple. Yes, I'm strongly avoiding that. The answer was, the comment was, use the builder and call it twice. And the first time use it to see what the size was, and then the second time use it to populate the size. That's what I did in 2016. I'm moving past this. Okay, so the idea is basically I do the work to make the oversized thing, and then I just have to copy the data a second time. I don't have to call builder twice. So, well, here, let's look at it. So, my to view takes the, okay, so I can make the Constexpr oversized thing by calling builder. We've already done that a dozen times. And then I just make another oversized thing, but now it is right-sized based on the compile time known size of the oversized thing. And so let me use my mouse pointer where I can get a little bit more accurate. The first template parameter is whatever the value type was of the first thing, so I don't have to do any of that work again. The second template parameter is oversized.size, which itself is now a constant expression. So I create the first thing that's oversized, then I create the second thing that's right-sized, and then I pass that to the view helper. Constant expression, static constant expression. Yes?
Stop the binary explode.
All right. The question was, how does this stop the binary from exploding in size? This thing, OS value on line 17, is the only part of this that persists into the binary. Remember, being Constexpr doesn't change the lifetime of the object. It just means it was computed at compile time. So all of that goes away. Only the final thing that I make static persists to the binary. So this is the fit it all in one flow on one slide. Again, I'm trying to make sure that I present this in multiple different ways so it makes sense. So I have my toSpan function on line 25 down at the bottom. Let's start there. I'm calling this thing, and I decided to make my, my builder slightly fancier. Now I initialize a vector, and then I do something with it. And I take that value, and I pass this up to my toSpan function. So I have an immediately invoked lambda that executes the builder and builds the oversized array, copying things in. And in this case, by the way, who said pass it as a pair, return it as a pair? In this case, I am returning as a pair because I removed my oversized array helper because I wanted it to fit on one slide. So this doesn't require anything else. This is all just standard library stuff that we're staring at. So I copy the things in, then I return a pair of the data plus the size. Then in this constant expression, I immediately invoked lambda. I now can treat the previous thing as a constant expression itself. I create the new right-sized array, I copy everything into it, and then this one is static. So now line 14, this is the static thing, and then I return a span into the static thing. And then I can print out the elements of the vector. So it's the Constexpr 2-step in 5 steps. But if I actually click on this, then I can see that this is exactly what persisted into the binary. The values 1, 2, 3, 4, and 42, which is the vector that I created. I am officially out of time. And we got through 3 levels.
Why?
All right. I really don't want to make you stay late. So I will move through this one faster, and we'll push it. I have this vector of strings of JSON was here. My options. I could have an array of arrays, an array of 3 arrays of 5 characters, because that is the max size of the strings. Just for the record, I used to do this particular version. I could return a tuple of array of car of 5, an array of 3, an array of 4. Or I could return an array of 12. This is the part where I really expected someone to argue with me. You like this one? What about an array of 15? Why? Null terminators. But I'm returning string views. And you can never count on a string view having a null terminator on those characters. So anyhow, this is bleh, an implementation of this. So I will just click on it real quick, and basically what I do is create a packed array of the characters. I have to loop through things twice. I call the worker once. I use it to create a packed array of the characters, but then I have to return all of the sizes of the individual strings, and then I have to construct the string view array of the sizes of the individual strings. And you can look at this later, but we can also just see the thing that persists to the binary was literally the string JSON was here. So this is all doable. And I will let you out in a second here. So, oh, sorry. Yes, that makes sense. You can go look at the Compiler Explorers. Have you heard of Compiler Explorer before? That's too late now. Oh, sorry. Everyone take a picture who would like to take a picture of the URL. I will stand out of the way. I am correct about the time, right? I'm now a minute past. Okay, just making sure. All right, so Our possible options are we work with only fixed-sized known things. This is how we did Constexpr before C++20, and it was annoying. Our second option is to work with dynamically allocated things at compile time and then copy those things into fixed-size things. It's basically what we did. Third option is to go the third step and right-size the fixed-size thing so that we avoid bloating the binary. And then the fourth step is creating views into the right-sized statically known things to simplify our use case. And if you can create views and spans into these things, then you can decouple your interfaces as well. And where you might currently be doing like a lot of compile time stuff and passing templates to templates to templates, if you do all of this work at compile time and the result is a span of string views, the rest of your interface doesn't have to know that any of this was computed at compile time at all if you don't want it to, or you can choose to let it be known at compile time and make all those things constant expressions usable in the other functions also. You can go either way with this. All right, and make things composable. Many possible approaches. I tried to vary it so that you had different views of the things. Prefer consteval to catch your bugs at compile time. Consteval is brilliant for this. I feel like most people use consteval thinking, I'm going to force the compiler to do work at compile time so that I know it's not done at runtime. Right now, I'm thinking I'm going to use consteval to prove my code correct by forcing it at compile time. Be aware of this consteval and static bugs with Clang. Static inside of Constexpr functions wasn't even added until C++23, but the rest of this can be done in C++20. And remember this trick, that by the way is the one-line example of making something static at compile time. Just pass it as a template parameter and return a reference back to it. Please don't try as hard as I did to make things fit on one slide. Aim for more readable code. If you want more inspiration, I'm going to wrap things up here. I have open source libraries where I do a lot of these techniques as well. And with my open source libraries, I have stuff like maps of vectors of strings working, and it gives you back a compile time known thing that's been right-sized. All right. Thank you, and sorry for running a little bit over, but if you want to know anything else about what I do, you remember here, take some stickers after the talk. Thank you, everyone.